In this session, we'll talk about congruences and some of its properties. So how do we define a congruence relation? Now we say that A is congruent to B mod M and write it in this way. A is congruent to B modulus M. If and only if A minus B is divisible by M. That is, A minus B must be divisible by n. So let's take an example. So we say that 10 is congruent to 5 mod 5. Right? So 10 minus 5 is 5 is divisible by the mod value 5. Also 12 is also congruent to 2 mod 5. That is 12 minus 2 is 10 is divisible by 5. So this is how we define a congruence relation. So let us see some of the properties of congruence relation. The first property states that A is congruent to A mod n. Right? So we know that A minus A is equal to 0 is definitely divisible by n. Now this is part 1 of the first property. Part 2 of the first property is that if A is congruent to B mod m, then B is also congruent to A mod m. Now when we talk about a mod value, if we say mod 5, then I have values ranging from 0 to m minus 1. 0 to m minus 1. That is 0 to 4 in this case. So if I take the example, 12 is congruent to 2 mod 5. So here we know that 12 minus 2 is 10, which is divisible by 5. Now interchanging these two, I also have 2 congruent to 12 mod 5. Now when I do 2 minus 12, I get minus 10. Minus 10 is invalid in mod 5 because we have numbers varying from 0 to 4. Now whenever we are operating in modular arithmetic, if I have mod 5 and if we get a negative number, what we need to do is we need to add the mod value m till we get the positive number, till we get the first positive number. So I go on adding 5. So 5 minus 10 would be minus 5. I add 5 again, so I get 0. So 0 is definitely divisible by 5 according to part 1 of the first property. So A is congruent to B mod m if and only if B is congruent to A mod m. And we know that if we get a negative number, we have to get its positive counterpart. How do we get its first positive counterpart? By repeatedly adding the mod value n until we get the first positive number. So let's see part 3 of the first property. Now it states that if A is congruent to B mod n and if B is congruent to C mod n, then A is congruent to C mod n. Right. If A is congruent to B and if B is congruent to C, then A is congruent to C. So let's take an example. 24 is congruent to 12 mod 3 because 24 minus 12 is 12 is definitely divisible by 3. Now let me take 12 is also congruent to 6 mod 3. 12 minus 6 is 6, which is divisible by 3. So this is A, I have B here, B and C. So definitely 24 is definitely congruent to 6 mod 3. Because 24 minus 6 is 18 is divisible by 3. Right? So part 3 of the first property is very clear, where if A is congruent to B mod M and if B is congruent to C mod M, then A is definitely congruent to C mod M. So we have taken an example. Now what does the second property state? The second property states that for a fixed value M, each equivalence class with respect to congruence modulo M has only one and one representative value between 0 to M minus 1. So we have already seen that if you are operating in mod M, then every congruence relation will have the final representative value which lies between 0 to M minus 1. So if we are operating in mod 5, I have the range between 0 to 4. If I am operating in mod 10, then I have the range between 0 to 9. If I am operating in mod 15, I have the range between 0 to 14 and so on. So let's see the third property. The third property states that if A is congruent to B mod N and if C is congruent to D mod N, then A plus or minus C is definitely congruent to B plus or minus D mod N. So let's take an example. So I have 48, which is definitely congruent to 6 mod N. Right? So 48 minus 6 is 42, which is definitely congruent to, well, the M value is not given here. So let's take the example of 3. So 48 is congruent to 6 mod 3. So 42 is divisible by 3. So let's take another example. 48 is also congruent to, I need another value for 24 is also congruent to 12 mod 3. So I have 24 minus 12 is divisible by 3. So these two congruence relations are valid. Now in this case, if I add A plus C, so A plus C is 48 plus 24 should definitely be congruent to 18 mod 3. Right? So 6 plus 12 is 18. So 72 should be congruent to 8 mod 3. So what does that mean? 72 minus 18 should definitely be divisible by 3. So we know that it is definitely divisible by 3. So 54 is divisible by 3. Right? So similarly, if I take the negative, 48 minus 24, that is A minus C, should also be congruent to B minus D. B minus D is minus 6 mod 3. So I get 24 is congruent to the positive counterpart of minus 6 is, so I go on adding the value of 3, that is the mod value to minus 6. So minus 6 plus 3 I end up getting 0 is congruent to 0 mod 3. So I have 24 minus 0 by 3. So 24 is definitely divisible by 3. So this proves the third property with an example. So let us take the fourth property. So what does the fourth property state? A is congruent to B mod M. If A is congruent to B mod M, then A is also congruent to B mod D for any divisor D divides N. So this is D divides N. So let's take an example. So we know that 48 is definitely congruent to 12 mod 12. So this is A, this is B, and this is M. So 48 is also congruent to 12 mod 3. So this is A, B, and D. So in this case we know that D divides N, 3 divides 12, or 12 is divisible by 3. So 3 divides 12. So definitely 48 minus 12 is divisible by 12, 36 is divisible by 12, 48 minus 12 is also divisible by 3. So then in that case D divides N. So 3 divides 12. So we have seen this with an example. Let's take the fifth property. If A is congruent to B mod M and A is congruent to B mod N and M and N are relatively prime, then A is definitely congruent to B mod M into N. So I have A congruent to B mod M, A congruent to B mod N, and if M and N are relatively prime. So we know what prime numbers are. A prime number is 1 which is divisible by 1 in itself. So 5 is a prime number, we know that 11 is a prime number, 13 is a prime number, and so on. So what are relatively prime numbers? Two numbers are said to be relatively prime if their GCD is 1. The common number which divides both is 1. So if I consider two prime numbers, let me consider 5 and 7. 5 and 7 is divisible by 1. A single number which divides both, 5 and 7, is 1. So two prime numbers are definitely relatively prime. Now let me consider the number 14 and 15. Now these two numbers are not prime. 14 is not a prime number, 15 also is not a prime number. But if I try to find the GCD of these two, a number which divides both 14 and 15, I end up getting 1. It was only 1 which divides both 14 and 15. So in such a case, these two numbers are known as relatively prime. So two numbers whose GCD is equal to 1, then those two numbers are said to be relatively prime. It means that it is 1 which divides these two. There is no other number than 1 which can divide the two numbers. So here we have considered two numbers m and n which are relatively prime. Let me consider n equal to 5, n equal to 6. So I find that these two numbers are relatively prime because GCD of m comma n is equal to 1, 5 comma 6. It is also to be noted that two consecutive numbers are relatively prime. Right? So we have to note that any two numbers, consecutive numbers, are always relatively prime. So that has to be noted. That's the reason why I have taken 5 and 6. So now we have 5 and 6. So n is 5 and 6. So I need to choose the value of a and b such that a is congruent to b mod m, b mod 5. A is also congruent to b mod n and is also congruent to b mod m into n. So mod 5 into 6 is 30. So I have 90 is congruent to 30 mod 5. Right? 90 minus 30 is 60, which is divisible by 5. I also have 90 which is congruent to 30 mod 6. So 60 is also divisible by 6. Now these two numbers are relatively prime. Then 90 is also congruent to 30 mod 30. So 60 is definitely divisible by 30. So we've taken an example here. So this condition is true only if m and n are relatively prime. Now use the congruence relation. Let us try to solve a few relations. So if I need to find the solution of the congruence relation 3x congruent to 4 mod 7. So how do I do this? I need to find the value of x. So this is a congruence relation. The value of x should be such that 3 into x minus 4 is divisible by 7. So 3x minus 4 is divisible by 7. That is the congruence relation. So how do I find the value of x? So very simple, x is congruent to 3 inverse into 4 mod 7. Now in a general relation, if I have 3x equal to 4 mod 7, we would write x equal to 4 by, if I have a general relations 3x equal to 4, so I would write x equal to 4 by 3 when we are not operating in mod. But since we are operating in mod 7, I cannot write 1 by 3 because the values would range between 0 and 6. So when we are operating in mod 7, I have values between 0 and 6. I cannot have any other value, so 1 by 3 is invalid. So I need to find the inverse of 3 in mod 7. I need to find the inverse of 3 in mod 7. What is the general definition of an inverse? I have a number a into its inverse should give me the identity element. A into its inverse should give me the identity element. So here 3 into another number operating in mod 7 should definitely give me 1 mod 7. So 1 is the identity element here. We are operating in mod 7. So 3 into some number in mod 7 should give me 1 mod 7. So by inspection, I know that 3 into 5, what is 3 into 5 is 15. 15 in mod 7. What is 15 in mod 7? I need to find its remainder. So 15 minus 7 into 2 is 14. So I get 15 minus 7 into 2 is 14, which is nothing but 1 mod 7. Right? So 15 mod 7 is nothing but 1 mod 7. So if the number is greater than the mod value, how do I get the answer? If the number is greater than the mod value, I need to subtract the given value with m so that I get a number within the range 0 and m minus 1. For example, if I have 10 mod 7, so 10 is not a valid number in mod 7 because I have numbers ranging from 0 to 6. So how do I get a number within this range? I subtract the mod value m from this number. So 10 minus 7 would give me 3 in mod 7. So 10 mod 7 is nothing but 3 mod 7. So similarly, 15 mod 7 is nothing but 1 mod 7. So 3 into 5 is giving me 1. Right? So A into A inverse should give me the identity element. 3 into another number is giving me an identity element 1. So therefore we conclude that the inverse of 3 in mod 7 is 5. So this is very important, which we need to remember when we try to find the inverse in modular arithmetic. So I have x congruent to the inverse of 3 is 5 into 4 mod 7. So I have 20 mod 7. So how do I get a value which is within the range 0 to 6? So I go and subtracting the mod value m from 20. So 20 minus 14 gives me 6. So x is nothing but 6 mod 7. So what is the general value? X can have any value 7n plus 6 in mod 7. Why is that so? 6 mod 7 is 6 itself. If I add 7 to 6, 13 mod 7 is nothing but 6 mod 7. So if I have a number 13 mod 7, it is congruent to 6 mod 7. So 13 is nothing but 7 plus 6. So if I go on adding multiples of 7 to the value 6, in mod 7 it is nothing but equal to 6. Right? So similarly 14 plus 6 is also congruent to 6 mod 7. So irrespective of the number here, where n of course varies from 0 to infinity, any number here which is a multiple of 7 added to 6 will always give me 6 as the answer. So x can have any value which is 6 plus 7 into n. So 7 plus 6 in mod 7 is also 6. 7 into 2 plus 6 in mod 7 is also 6, and so on. Now in this problem, we had to find the inverse of the number 3 in mod 7. Since it was a very small number, we could find the inverse by inspection. Now suppose I need to find the inverse of 102 in mod 213, for example. I need to find the inverse of 102 in mod 213. It is not possible for me to find the inverse by inspection. So how do we find the inverse? We will see that in the next session, where we use the extended Euclidean algorithm. The Euclidean algorithm extended to find the inverse of a given number in any mod value